Hello, am I audible properly right now? Hello?
Yes, ma'am. Now,
Okay.
yes,
Actually, I am
ma'am.
facing power cut. That is why I got disconnected. So I am starting the
Okay,
presentation
no issue.
afresh. Just 1 minute. Okay. So I am sharing my screen once again. So my screen is visible right now. Hello, my screen is visible.
Ma'am,
Okay, so I'll be trying to explain different QML applications, particularly in medical domain or healthcare domain. So so why machine learning is so significant? Actually, machine learning methods can handle voluminous data, and all those voluminous data can be categorized into different classes by machine learning algorithm. This is the significance of different machine learning, why the machine learning algorithms are so significant, so important. That is the reason. And why quantum computing is very important, or the quantum computing is very significant. That is, quantum computing actually relies on two inherent quantum computing properties. Those are called superposition and entanglement. For these two inherent properties of quantum computing, actually quantum computing is very much significant. I'll be explaining in due course of time. And we are amalgamating these two technologies, that is machine learning and quantum computing, to get a new technology, that is quantum machine learning. And why quantum machine learning is so important, that is the significance of quantum machine learning is that it actually exploits the two significant properties of quantum computing, that is superposition and entanglement. By the superposition properties of the quantum computing, quantum machine learning actually is able to represent able to rather process 2 to the power n possible states at a time if the number of input qubits equal to n. That is the benefit we are getting out of the superposition property of quantum computing, number 1 point. And number 2 point is that in quantum machine learning, we also exploit another quantum computing property, that is entanglement. By this entanglement property, quantum machine learning models actually can capture the intricate patterns and feature correlations in the quantum feature domain. That is why quantum machine learning models have got so much of importance, have got so much of concentration of the researchers right now. So we'll be seeing the in due course of time the applications of quantum machine learning in the healthcare domain, because in the healthcare domain we actually face a huge volume of medical data, and by properly analyzing those medical data, huge volume of medical data, we can provide better treatments to the patients. So before entering into the formal discussion regarding the execution of quantum machine learning or quantum computing and the application of quantum machine learning or quantum computing, I want to discuss briefly that what are the different applications, means how quantum computing can be utilized in the medical domain. In the slide that I am showing right now, this particular paper actually involves in diagnosis of brain tumors or abscesses or cysts. This is one of the applications of quantum machine learning. Similarly, in this journal article involves analysis of COVID-19 images. Similarly, this particular journal article also predicts COVID-19 affected images. And this particular article, it actually detects stenosis from the X-ray coronary angiography. And this is another classical quantum convolution neural network which deals with pneumonia detection and this particular paper deals with the detection of lymphoblastic leukemia from the blood cells. So what we can infer from all those papers we have just now seen, all those papers have published between 2022 to 2024. So what we have seen from all those papers, that these papers are actually indicate that quantum machine learning can be utilized in the medical domain, means for diagnosis of different diseases, for the benefits, for the patient benefits, etc. So before entering uh, into the our work regarding application of quantum machine learning in the medical domain, I would like to show some of the quantum circuit execution. In Professor Devashish's slide, we have seen that Bell circuit, that is the very fundamental quantum circuit, that is 2-qubit entanglement circuit. Similarly, another very fundamental quantum circuit is G8Z circuit, that is a 3-qubit entanglement circuit. So we are for the time being we are choosing the G8Z circuit, that is one of the fundamental circuits, that 3 qubits. What we can see from the slide, that there are three qubits. Qubit 0 is passed through Hadamard gate, different gates. Professor Devashish has discussed different gates, logic gates, quantum logic gates we can utilize for preparing the quantum circuit. Here, for preparing this fundamental quantum circuit, three qubit entanglement circuit, the qubit 0, that is passed through Hadamard gate, and qubit 1, that is the qubit 0 and qubit 1. These two qubits are entangled with C0 gate, and qubit 0 and qubit 2, these two qubits are entangled with another C0 gate, and all these three qubits are measured. So we can understand from the diagram what actually the fundamental G8Z circuit is. So I would like to execute this particular circuit, and we'll be measuring all the outcomes and what is the result, what is the output we are getting out of execution of that quantum circuit, that can be seen from this execution. So we are executing the simulator. So this is the this particular interface is not free right now. Previously this particular interface was free, but this particular interface is the IBM Q interface. If we log in the IBM Q interface, and we can be utilize these types of notebooks are available where we can write the program using Python language, and we can execute simulator as per requirement. We can execute simulator, or you can you can access the quantum hardware also, that is your circuit you may execute in simulator as per your requirement, or you may execute the quantum circuit in the quantum hardware also. So this is the particular IBM Q interface. With this first code cell, what we can see over here, that different required Qiskit libraries, we are implementing the Python based quantum computing language using Qiskit. We are implementing all the codes using Qiskit, that is a Python based quantum computing interface framework. So from Qiskit, we are in the first code cell, we are importing all the required libraries. And the Qiskit service we are trying to access from IBM Quantum. Now, if we are moving forward, so after executing this particular code cell, all the libraries will be imported. After that, we are trying to create the circuit, that GHZ circuit just now I have discussed, that is a 3-qubit entanglement circuit. We are trying to create that particular circuit with quantum register. We are inside the quantum register. We are passing 3 qubits, and the quantum circuit object, inside the quantum circuit object, we are passing that particular quantum register to create the quantum circuit object. Now, that name of the quantum circuit object is QC. If the quantum circuit object is created, QC is created, then QC is added with one Hadamard gate, and that Hadamard gate is passed through qubit number 0. After that, we require, as we have seen previously, after that we require 2 C0 gates. These 2 C0 gates will be entangle 2 qubits. That is, first C0 gate will entangle the first qubit and the second qubit, that is QR0 and QR1, and the second C0 gate that will entangle first qubit and the third qubit. And we are measuring all the qubits using the function measure all. After that, the QC object, I want to draw the QC object using the draw function. Within the bracket, I am passing the parameter MPL. MPL stands for matplotlib, so that we can use the matplotlib library to draw the circuit. So that we can visualize the circuit. So this is the circuit we have created. In the slide also we have seen this particular circuit, that is Hadamard gate, 2 C0 gates, then all the qubits are measured. This particular circuit has been created using Qiskit inside the IBM-Q environment. After that, we are trying to execute this particular circuit. So in the next code cell, we are trying to execute that particular circuit using the simulator, where I have written that shots equal to 1000. That is, the experiment will be repeated for 1000 times, and among all those 1000 times repetition, how many times which outcome we are getting, how many times, that can be computed with the gate counts function. Which output we are getting and how many times we are getting each of the outputs, that is obtained by this particular gate counts function. And we are trying to plot the histogram using that counts variable. So what is the histogram we are getting from that plot histogram? That is, as we have executed the circuit inside the simulator, what we can see here, that we are getting two outputs, that is absolute 0 and absolute 1. But how many times we are getting absolute 0 and how many times we are getting absolute 1? That is 490 times we are getting absolute 0 out of 1000 shots, and 510 times we are getting absolute 1. If we can recollect this particular output, then we'll be able to understand what is the difference with what is the difference between the execution of the same circuit. Difference means the difference between execution of the same circuit in the simulator and in the quantum hardware. What is the difference? So if we can recollect this particular output, in the next phase I'll be showing you the execution of the same GHZ circuit in the hardware. So we'll be able to understand what is the difference. So the same execution environment I'm currently using, that is the IBM-Q environment. But what is the difference? This time we are trying to execute the same circuit inside the quantum hardware. That is, we are trying to access the QPU, quantum processing unit. So the same circuit we are creating, all the required libraries are already imported. That is why I have not written the import statements, only I have imported the quantum circuit object. And inside quantum circuit object, again I am passing 3, means I am passing 3 qubits, and Hadamard gate is applied to the first qubit, and control not gate is applied to the first and second qubit, and control not gate is applied between first and second qubit, and all the qubits are measured. And similarly we are trying to draw the circuit that we have created through matplotlib library. So what will be the circuit diagram? We can see the circuit diagram if we have executed this particular code cell. So this is the particular circuit diagram. This particular circuit already has been created. Now in the next code cell, we are trying to execute this particular circuit, but this time we'll be executing this particular circuit. Note it, this time we'll be executing this particular circuit in the uh, quantum processor. So for that, we are trying to uh, with this code cell, particular code cell, we are trying to know the status of all the backends. Means the backend means the backend QPUs. What are the status of all the backend QPUs are available backend QPUs, that will be stored in a dictionary, and that dictionary will get printed. So after executing this particular code cell, the status of all the backends available will get printed. And if we note the output of that dictionary, we can see that these are the, say for example, this is the dictionary that has got printed. This is the dictionary, and if we say concentrate in one of the rows of this output generated, say this is one of the row, then what we can observe here, please concentrate on the line. What we can observe here, that the backend name is IBM Kyoto, that is the IBM processor, quantum processor, that is available in Kyoto. That particular processor is available, and the operational flag of that processor, Kyoto processor, is true, means that IBM Kyoto QPU is operational currently, and that is the status of the IBM Kyoto QPU. And the number of pending jobs, as sir has mentioned during his presentation, that each and every IBM, any service providers QPU, each and every QPU is associated actually with a queue. When we are submitting job to for that processor, that job will get stored inside that queue, and all the jobs are queued up, and one by one the QPU services, providing services to all the jobs. So here this particular Kyoto processor is operational, and number of pending jobs in the associated queue is equal to 2. That is only 2 active jobs are there in the associated queue. So these are the status of all the backends. And see, in this particular third row, if we observe, that is simulator stabilizer, means these are the simulators. These are not actual hardware processors. These are a first row. This represents one simulator. Second row also simulator, state vector simulator, and third row is another stabilizer simulator. So these are not actually hardwares. These are actually simulators. But with this execution, we want to access the hardware. We are interested about the hardware execution. So in the next cell, what we are doing, we are actually trying to know look at the next code cell. In the next code cell, we are trying to know among all those resources that are shown from the dictionary, which particular resource is list busy by using the function service.listBusy. And I have written the simulator for the flag simulator equal to false because I am interested to execute the quantum hardware, not the simulator. That is why. Similarly, the operational flag I have written equal to true means only I am interested about the operational QPUs. That is why. And after that, print backend. So this information will get stored inside the backend and the backend will get printed. So what does it print? What we can see that it is printing that particular, which it will be printing the particular IBM Kyoto, that is this particular IBM Kyoto, which has only 2 numbers of pending jobs in the queue. It actually prints the name of that list busy quantum processor. Now, in the next code cell, what we are trying to do, we are trying to execute that. We are trying to access that backend, and uh, that particular hour circuit that is stored inside the QC object. That QC object we are trying to execute inside that backend, that is the Kyoto backend. So, okay, so preliminary we have set the number of shots equal to 1,000, but it is not taking. It is telling that got an unexpected keyword argument shots, because we are getting this particular error because the number of shots that is by default set for Kyoto hardware, that is equal to 4,000. That is why we cannot set explicitly the number of shots. That is why it is giving some error over here. So if we do one thing, we are just removing that particular argument and executing that code cell once again, so it is executed properly. Now we are trying to show the status. So the job has been allocated to that particular hardware. Now we, with this particular code cell, we are trying to see what is the status of the job. So the status of the job, it is showing that the job is actively running. The status, it is showing that the job is actively running. Now, if if we want to execute this particular job dot status once again, yes, this particular job is running over here, and the status timeline, it is showing that the job is completed. In between, if we want to execute, it has taken 14.1 second. So if we want to execute this particular code cell once again, job dot status, previously it was showing that job was running. Now I am executing job dot status once again. So it will show that job has successfully run. The status has been changed. Now with the next code cell, what we are trying to do, we are trying to execute that particular circuit. Now please recollect that previous output, because I am executing the same circuit. So if you are able to recollect that previous output, you can see the distinct difference between the previous output and the current output. But what is the input? The input is the same. That is the same circuit we are executing both in the simulator and in the quantum processor. But previously we have got outputs that is absolute 0 and absolute 1. But here if we notice that we are getting different outputs, that is all the possible outputs, the major major outputs are absolute 0 and absolute 1. We are getting 1733 out of 4000 shots. 1733 times we are getting 0 as output, and 1616 times we are getting absolute 1 output. But all the other possibilities are also there. So these particular different combinations we are getting, also we are getting these different combinations, but majorly we are getting absolute 0 and absolute 1. So as we are running our circuit, executing our circuit in the quantum processor itself, that is why, not simulator, that is why it is showing all the possibilities of getting different outputs. So so now this particular graph is visible. That is absolute 0. We are getting absolute 0 1733 times. Absolute 1, that is the major outputs, 1616 times. But all the possible outputs are also present. Means only 230 times we are getting 001 output. That is, the probability is much less than these two outputs. So that is the difference between the execution of these two circuits in quantum processor and the simulator. So after this, what I would like to show you that I would like to show you the same circuit we are trying to execute in AWS simulator as well. It means the all the access, means access to the IBM quantum processor, or access to the two different types of quantum, because in AWS is the service provider. So we can access different types of quantum processors through AWS. So many quantum processor providers, they provide access to quantum hardware through AWS platform. We can choose any of them. So I'll be logging in the AWS account, and I'll be showing what are the devices available inside the AWS platform. Means Amazon, what are Amazon is providing, what are the different QPUs we can access through Amazon interface. So that I will show. Before that, please look at this. This is the Amazon bracket interface. What we can see from here, this is the Amazon bracket interface, and Conda bracket is running over here. That is the kernel, the name of the kernel that is running inside Amazon bracket interface. Means the different, actually AWS provides different types of services, and the quantum service, particular quantum service AWS provides, that quantum service is called bracket service, and the kernel here is, the kernel that is running here is Conda bracket kernel. So in this bracket interface, what with this first code cell, what we are trying to do is, from Qiskit bracket provider, that is we are importing AWS bracket provider. And then what we actually want to know is the status of the backends. In case of IBM Q interface also, I think you can remember that we wanted to know the status of different backends, and that dictionary was shown. That is, dictionary was reflecting the status of different backends available. Similarly, with this code cell in the AWS platform, I'm trying to know the status of the simulators, that is backends, backend types. What is the backend type? Previously, we selected the backend type was QPU hardware. Here I am trying to select the backend type equal to simulator, and the status of the backend is equal to online. So if we run this particular code cell, what is the output we are getting? That it is showing the what is the output it is showing? I'm explaining that the output it is showing is that three different types of simulators are available. Actually, three different types of simulators AWS provides. This one is SV1, that is state vector simulator. This one is TN1, that is tensor network simulator. And this one is DM1, is the density matrix simulator. Now, according to the user requirement, whether I want to use the state vector simulator or the tensor network simulator or the density matrix simulator, according to the user requirement, I can use one of these three AWS simulators. So different quantum simulators are available, but explicitly AWS provides only these three types of simulators. So these three types of simulators are online right now. It is showing that all these simulators are available. So we can select any one of them. Now we are selecting tensor network uh, because we are trying to execute one, say for example, for QML execution, uh, because we are very much familiar with execution of tensor network, because if we execute a quantum machine learning model, in many of the cases a network is created, and if we create the tensor network, in that case the TN1 simulator, we are very much familiar in using the tensor network simulator. That is why I have just arbitrarily selected any one of them. TN1 I have arbitrarily selected. So if we execute this particular code cell, now this particular code cell is executing. So that particular TN1 is now available to us. Now in the next code cell, what we are trying to do, we are trying to create the same circuit I have shown you in the PowerPoint slide, that is the GHZ circuit, that Hadamard gate, CNOT gate, CNOT gate, and we are creating that particular circuit, and we are after creation of that particular circuit, we are trying to draw that circuit. So after execution, just we have created the circuit and we are trying to draw that circuit. So this particular circuit has been drawn inside the AWS interface. Now what we are trying to do, we are now trying to run this particular circuit. For that, because we have now we have accessed the TN1 simulator, that AWS TN1, we are running AWS TN1 simulator. With that particular circuit we have created, and I have mentioned here shorts equal to 10, because AWS platform is very much costly. That is why, and the cost of Devashish Desai also has mentioned that the cost of AWS service is very high. That is, it demands the cost of per quantum task, per shot, and per minute. Something dollar is associated with that. For that reason, I have only mentioned that the number of shots equal to 10, and the task ID we are trying to retrieve, then that task ID will get printed. That task ID we are trying to retrieve because we want to print the result by accessing that task ID, means result of which task, that can be mentioned by the task ID itself. So we are trying to execute this particular code cell. Now this particular code cell is executing and the task ID gets printed. This is the task ID. By this task ID, we can access the quantum task, the result of the quantum task. Now, the retrieve task equal to we have the task ID. So if we write the task ID equal to task ID in this variable, this particular task ID is stored. So if we mention this particular task ID within this bracket, then the retrieve task variable will be able to show the status of the task right now. So this particular code cell is now executing, and the status of the job, it is showing that the status of the job. If the task ID is not available, then the status of the job will not be able to show the status of the job. That is job dot status equal to job has successfully run. That is the circuit has been allocated to the simulator, and the job has been successfully run. Now with the next code cell, what we are trying to do, we are trying to do the same thing we have done for IBM-Q interface. That is, we are trying to plot the histogram, and we are trying to get the counts of each output. And mind it, we are using simulator in AWS. Again, we are using simulator in AWS interface. So with get counts, we are getting the number of times we are getting a particular output. So this is the output. As we are using simulator, major outputs we are getting, that is absolute 0 we are getting 42 times, and absolute 1 we are getting 58 times. So this is the output we are getting when we are executing this particular circuit in AWS simulator. So we have seen, so if the time permits, I will be showing the execution through AWS hardware, through AWS platform. I'll be showing the execution, hardware execution also through AWS platform. So before moving to the next phase, what I want to show that, say I want to this one is the AWS interface. So if we want to log in the AWS interface, so I'm logging in by providing the password. I'm logging inside the AWS platform. So we are logging inside the AWS platform. This is the AWS platform, and what I have previously mentioned that different services are available. These are the different services AWS is providing. So many view all services. If we do view all services, it will show here all the services. So many services are available through AWS. User can access so many services, and among all those services, only among all those services, only the Amazon, we are interested about Amazon bracket service, because this particular service, if we create AWS login, this particular service will not be available. This particular service is paid service. So only if we subscribe for this bracket interface, then only this particular service will be available on my AWS dashboard. So if I click Amazon bracket, we are entering inside the bracket interface. So this is the bracket interface where it is showing different news as announcement, means different quantum processors which are now available, etc. Now all the menus are available over here. Say for example, Devashish sir has explained what the hybrid jobs are with respect to QML. Actually, some part, that is the circuit execution takes place. Please listen carefully. The circuit execution is actually taking place inside the quantum processor, quantum hardware. But with respect to quantum machine learning, if we want to adjust the parameters, if we want to optimize the parameters of machine learning model, in that case, we need the help of the classical processor. That is, the optimization process takes place inside the classical processor. That is why these type of machine learning models are actually called, these are actually called hybrid jobs. So here one menu is available, that is the menu is called hybrid jobs. If we click on that menu, so we are see one thing, I have logged in, and this one is the this particular drop down menu shows different regions, huh? And I have logged in the California region. If I in the North California region, I have 4 hybrid jobs, and among all those four hybrid jobs, 3 of the hybrid jobs we have completed, but one job was anyhow one job was failed, was not completed successfully. But if we switch the zone, say for example we are now executing in North California zone, if we switch the zone, that is if we execute in North Virginia zone, I'm switching the zone right now. So this is the this particular drop down menu. It is showing that we are now highlighted zone is North Virginia. So in the North Virginia zone, I have many hybrid jobs. Some of the jobs are completed, some of the jobs are failed, some of the jobs are cancelled, etc. So different hybrid jobs, it is showing the interface. And notebooks, if we click another menu, notebooks, that is different notebooks, means the Python notebooks we have created using, you have to use the Python language and the framework quantum computing, different quantum computing frameworks, those are available. For example, Google Shark, for example, Penny for example, Qiskit. So these any of these quantum computing frameworks you have to use to write this type of notebooks, Python notebooks. And what are the different quantum tasks? So these are the different quantum tasks that is completed. So if we click to the, that is next page will be shown, that is within a quantum job, so many quantum tasks are allocated to the quantum processor, and all those updates are available in these different pages, 1 2 3 and so on. All those updates are available. And similarly, if we click another menu, that is devices, devices, all the, what I have told to you, that 3 different simulators actually AWS provides. One is state vector simulator, tensor network, and density matrix simulator. So these 3 simulators, it is showing that these 3 simulators are online. This is 34 qubit Amazon bracket state vector simulator. This is 50 qubit Amazon bracket tensor network simulator. And this one is 17 qubit Amazon bracket density matrix simulator. All the status of all those simulators are online. Means if you want to use those simulators, currently these simulators are available to the users. If I want to use, I can use it right now. Now, what we can see from IonQ, IQM, QERA, Rigetti, etc. are the different quantum processors currently, but all the quantum processors are not available right now. IonQ area 2 is offline. That is, if I want to access IonQ area 2, this is not available to me. Similarly, if I want to access Rigetti Aspen M3, then Rigetti Aspen M3 is offline. So I cannot access IonQ area 2 or Rigetti Aspen M3. Instead of that, other quantum processors are available to the users. Another thing we should note over here, that IonQ41, this particular quantum processor, is available to the user only by reservation. So if I want to execute IonQ41, I have to reserve the slot, and IonQ41 execution is very much costly. In comparison with other quantum processors, IonQ processors are, 3 IonQ processors are here. IonQ processors are more costly. Why IonQ processors are more costly? Because IonQ provides error mitigation circuits as well. Though the error mitigation circuits are actively working if the number of shots equal to 2500, not less than that. Uh, so INQ processors are costly. That is, the per task, per shot, and per minute cost of INQ processor is higher than other processors. Another thing is to note over here, that is Q-era is a one type of processor from Aquila device. That is, QERA is the analog neutral atom based QPU. That is, all the quantum processors, all these quantum processors are digital QPU, but QERA is the only analog QPU that is available to the users right now. So, if time permits, I can show you the execution in this uh, quantum processors as well. So before showing you the execution, uh, I want to show you some of the tasks that we have executed. That is, some of the applications. I think the application of QML is um, visible to all of you. So this particular paper, the name of the paper is Federated Quantum Neural Network for Privacy Preserving Early Detection of Diabetic Retinopathy. This particular paper is very recently got published in the September 2024 in Evolutionary Intelligence, and this work is funded by Ministry of Electronics and Information Technology, Government of India, and is supported by Amazon Web Services for the bracket interface they provide for execution of quantum computing programs. The principal investigator of this particular project, this project is an ongoing project. We are currently working in this project, and so many works are there in the pipeline. The principal investigator of this project is Professor Debashish De from Mahua, West Bengal, and co-PI is myself, Dr. Mahua Nandipal from MCKV Institute of Engineering, West Bengal. And as the introduction of this particular paper, what we can say is that diabetic retinopathy is one of the leading causes of blindness in the diabetic patients. And early detection of diabetic retinopathy is very crucial for preventing the irreversible changes that takes place in the eye during the progression of this particular disease. That is number one point why we are interested to do this type of work. And why we are applying quantum neural network, because quantum neural network offers some potential advantages over the classical neural networks. That is one point. That is why we are interested to implement quantum neural network for this particular task. And another point is, one of the major concern in the medical domain or healthcare domain is to preserve the privacy of the patient data. That is, patient data privacy is a major concern. So we have implemented federated learning. Sir, Devashish sir has mentioned regarding the federated learning also. So we have implemented the quantum neural federated version of quantum neural network that preserves the privacy of patient data through distributed learning. So as the introduction of the work, I can mention these 3 points. But what is the motivation of this particular work? The motivation may be the quantum neural network. Quantum computing has two inherent properties that I have already mentioned, that is superposition and entanglement. And superposition provides, as I have already explained, why superposition provides parallelism in computation. Already I have mentioned that why entanglement is beneficial for this type of work, because entanglement, I have explained earlier, that entanglement actually helps us to capture the intricate patterns and feature correlation. That is why entanglement and superposition are very much important. And the quantum feature space, the quantum effective quantum feature space is obtained through quantum entanglement, and by that way we can generate a powerful model with limited number of samples and limited number of learnable parameters, as the model use very few number of learnables, very few number of samples and training samples, and very few number of learnable parameters. So the model is very much computationally efficient as well as faster. And also that I have already mentioned, that collecting sensitive data in a central repository that poses risk of data breaches and unauthorized access to the data. So to prevent those type of data breaches or unauthorized access to data, we are adopting distributed learning, that is federated learning. So this is the two-dimensional image, and we can extract the healthy patch from this one. Is the healthy patch, one hemorrhage dot we can see over here. So this one is the unhealthy patch. We can extract this type of execution. Devashish this has explained. So we have executed this type of this is the system we have implemented. These are the edge devices, that is the mobile phones, tablets, laptops or desktops through which the that is mobile phone enabled retinal image capturing fundus cameras are nowadays available, or any other camera, special purpose camera we can install with the desktop or laptop or other edge devices, through which the two-dimensional fundus retinal images can be captured, from which the patches can be extracted. And through amplitude encoding, this classical data will be converted to quantum data, and after that the local models will be trained, and from that local model the federated model will be trained. This federated model will be able to two-dimensional arrow, both directed arrows are over here, that is local model parameters are going to the global model, and after the federated model is created, the global model is returned back to the local nodes. Local nodes means the hospitals, hospitals or the diagnostic centers, etc., where the evaluation of that global model is taking place. So this is the outline of the system we have created. This is the result that we have obtained, that is the before applying federated learning. These are the results after applying federated learning. These are the results. These are the three local models, three local medical centers where we are obtaining these results. And the evaluation metrics we are using: accuracy, precision, recall, F1 score, and specificity. And these are the different that is epoch versus non-FL accuracy. We have used three different types of optimizers, that is Adam optimizer, nested of momentum optimizer, and gradient descent optimizer, and three different graphs we are getting out of that. The blue graph is most stable, and that blue graph is obtained from Adam optimizer. So we have we have adopted the execution through Adam optimizer. So this is the same thing we are that is the this one is the non-FL version, and this one is the FL version. Here also we can see the blue graph is the most stable one. So epoch versus non-FL accuracy, we can see this one is the blue line is the training accuracy and in the quantum model, and green line is the validation accuracy. Similarly, training and validation accuracy for the case of FL model, what we can see over here, the global model is more stable than the local models, because the global model is the generalized model. That is why we are getting more stable graphs over here. And these are the comparison, that is non-FL quantum model is the blue line, green line is the non-FL classical model, FL quantum model and FL classical models, and the accuracy of all these four different types of models, and the loss of four different types of models for non-FL quantum, non-FL classical, FL quantum and FL classical model. So many results are there. Some of the results I have shown to you over here. So thank you for your patient hearing. So if you have any question, you can ask the question to me. Thank you, everybody.
Yeah, thank you so much, Mahu ma'am. As we
Yes.
conclude this, am I audible?
Yeah, you are
Yes.
properly audible.
Yes. Anyone wants to say something? Yeah, okay. So as we conclude the insightful session, I'd like to extend our sincere thanks to appreciate the efforts put in by both of the first Dr. Devashish, then Dr. Moha for sharing their deep expertise on quantum computing. Dr. Devashish, your detailed explanation starting from the basics of quantum computing to the concepts like quantum dots and how quantum computers actually work and how the things work, and has given a solid understanding of information technology. Your approach was comprehensive and engaging, and we are really grateful for the clarity you brought to us from this complex subject. You brought us to the lamp of creative, like we got some of the things like we should learn about quantum computing, and also a very special thank you to the Dr. Mahua for her fascinating insights into how quantum computing can be applied in the medical field. Also, ma'am suggested that also explained very deeply that how the things actually work on the AWS simulator. That was the best part, and also the insights that I think we can take from this is that superposition and entanglement. These both are the major forming of the quantum computing. And Dr. Mahua, ma'am, your discussion opened our mind to incredible potential that quantum technology holds in revolutionizing healthcare and medical research. On the behalf of our institute, also everyone present here, thank you so much, both of you, for your valuable knowledge. And yeah, thank you for your time and efforts. Thank you so much.
Thank you. Thank you.
Thank you, everyone.